Right, thanks everyone. I've been working on something at work for a while, and this talk is going to be half, I guess, like a introduction to the idea of architecture diagrams, and then the second half we actually get into some code and get into write Haskell and stuff like that. But the first half is not about functional programming or Haskell or anything. So if you're really into functional programming and you don't really care about anything else, well, first half of this is not really for you. So the reason why I want to talk about architecture diagrams is I've been working on a team at Atlassian Marketplace inside of Atlassian, and we had a project where we had to move the team from San Francisco to Bangalore. We're spinning up a Bangalore office in India, and we needed a project to give to them to kind of build an office around. And Atlassian Marketplace, which was the team I was on at the time when this decision was made, was decided to be the team that was moved to Bangalore. So the interesting thing about Atlassian Marketplace is that it's actually 100,000 lines of purely functional Scala code. So it's it's a very, I guess, like for people that aren't familiar with functional programming, it's a very intimidating code base to get onto on that. And so it takes a bit of learning to get into it. We have to do a lot of training on people. There's just basically a big investment to get people to work on this, 100,000 lines of purely functional Scala code to make Atlassian Marketplace. So we've built this team around it, and one of the important things is the idea that communication is really key when trying to work on things like incidents. For example, like if the website goes down, if Atlassian Marketplace goes down, there's many different systems involved. There's probably like 10 that kind of immediately involved, and depending on the type of incident that we're having. It really can really affect what systems are involved. And so it takes a while for us to kind of communicate and say, this system could be the thing that's brought down the website, or that system could be the one. And also, code just takes a while to read. If you're not familiar with 100,000 lines of purely functional Scala code, it can be quite difficult to kind of get used to jumping into that and reading it. And you don't really want to be doing that during an incident. When you're trying to bring a website up, every minute counts. And so you want to have something that you can quickly use to communicate and quickly use to express, where problems can be, rather than digging into code, digging deep. You don't really want to dig deep during an incident. You want to have like a kind of a broad understanding of things. You don't want to be going really deep into things. So architecture diagrams is a way to communicate, I think, around how software works. And I've been to conferences before and I've asked, who uses architecture diagrams? I've been very surprised. There's been very few people that actually use architecture diagrams to, in their business. I imagine, like I have worked at small companies before as well. Atlassian is no longer a small company. When I joined, we're 300 people. Now we're very different. We're about 5,000 people. So I have worked at smaller companies as well, though. 10 developers or so. And we didn't really have architecture diagrams from what I can remember. I feel like maybe architecture diagrams kind of come up at the point where you have a large company and you're working on 10 different systems at once, instead of just working on one system at a small company, which usually happens. So maybe it makes sense that most people don't really use architecture diagrams, but if you're at a large company, I would imagine you're already using architecture diagrams. And I do think that even for small companies, it can make sense. I've used architecture diagrams to propose changes. So we've had different systems involved. We've used like different systems that do authentication, and I've proposed let's change our authentication mechanism to use this authentication mechanism. And so it's just a way of kind of at a high level proposing changes, and people can more easily see what you're actually proposing if you circle out what's going to be cut out and what's going to be replaced with. And failure points during incidents really important. I've been in teams in rooms before where there's an incident happening, and people are arguing over whether the incident is happening at this layer or at this layer or this layer. Which layer is the which layer of communication is the failure happening at. And by putting an architecture diagram in front of everyone, we can pretty easily say, these are the symptoms that we'd see if this was the problem. These are the different symptoms we'd see if this is the problem. So it must be this thing because we're seeing these symptoms. So it's really, I guess, like a really useful tool for getting people to focus on what you want to focus on. If you are saying, these symptoms must be, or these symptoms are occurring, so it must be this thing. Once you put an architecture diagram in front of people, they can actually be convinced. Whereas, without architecture diagrams, and then I've seen these things go over in circles and circles and circles, not really progressing. And also, I've also found them useful for talking about user experience. So someone will propose something, we need to put this system in, and it sounds great. But then you start thinking about like, how will the user see that data that's in this system? And so then you'll have to like trace the flow back of like, the data's down here, how will it flow throughout a system so that the user can see it? And so you can actually talk about user experience and say, well, if we do this in a naive way, we probably won't have a good user experience because all this data won't flow through. We'll only have a partial view of the data. And so the user will get an error message saying, the underlying system didn't work. And you'll be like, well, what does that mean? So I do think also it can be useful for user experience. And, I'm sure there's other uses of architecture diagrams. These are just ones that are, pretty vivid in my mind as uses. So if you don't get anything else from the talk, I want you to get this, which is, I think architecture diagrams are super useful. Yeah, I use them a lot at work. It's become quite a bit of my job. And I don't want to, I think when I talk about architecture diagrams, a lot of people my age and older, or at least with learning about this stuff back in, 2000s, a lot of us think about, UML diagrams and class diagrams and package diagrams. And that is definitely not what I'm talking about. I've never found a real use for UML diagrams. I don't find them useful at all. What I do find useful, the reason why I don't find UML diagrams useful is because, it goes into too much detail. It's just way too detailed. I don't really care what fields you've got on your class. I don't care what classes you've got involved even. So I've mainly focused on, system diagrams, sequence diagrams. I have found state diagrams and network diagrams to be useful as well, but the first two, system diagrams and sequence diagrams, are the one that I'm gonna show off a little bit in this talk. And I'll just show some examples of the type of diagrams that I do find useful. This is the diagram that we used to give Atlassian Marketplace when we were transitioning Marketplace from San Francisco to Bangalore. This is really the thing that we kept referring back to over and over and over again. This shows all the different systems that are involved in Marketplace. Doesn't really show there's a lot of arrows here, and doesn't really show the relationships between them. You have to really know some of the context. Like for example, here you've got something called Atheros, and then you've got AMKT, and then AMKT has something like Confluence Cloud or something as backend. And why is Confluence Cloud talking to AMKT, which is talking to Atheros? There's no context there in those arrows. So there is a little bit of explaining to do in each one of these, but it's a pretty good diagram in that it does show all of the different systems involved. There's a lot of different icons, a lot of different colors and stuff going on as well. That there's no legend as well, you can see. So you kind of have to guess what each of those means. But I think this is a pretty good diagram. It does show all the systems involved, and it was very useful while we're transitioning the team from San Francisco to Bangalore. This was extremely useful, and it still is useful today. We still maintain this and keep it up to date, and we refer back to it during incidents and stuff. So it is useful. This is a sequence diagram. So it shows you like the flow of communication between different systems. This is actually quite detailed. This one goes quite deep into the code. So we've got like a client that connects to an API, and then you've got a pricing model, and then mHamlet. mHamlet is actually like it's a monad, what we call in Scala. So it's actually it's actually quite detailed, this thing here. But it basically shows the flow of calls throughout this program. So you don't really have to dig deep into the code and kind of jump through all the references and stuff like that. If you can create some high-level diagrams like this, without actually showing the code, it can be useful for you to see, what different, bits of code are involved when you make a call. So this is a nice one. This is one actually I got this week. It was very interesting. I got a pull request from one of the grads that we hired last year. And he, in his pull request, did the really awesome thing. He submitted a sequence diagram with it, which I thought was absolutely amazing. So, he just wanted to show, how the code is now working, after his pull request came in, which is really cool. So you can actually review his pull request and also know the flow at a high level. You can look at the flow without digging deep into the code and trying to understand all the code and keeping that in your head. You can just look at the sequence diagram, which I think was really cool. I wish all my pull requests came with sequence diagrams. I think that'll be really nice. And this is one that I made. This is, I've been working with like a new system that we're trying to incorporate. And this is just like a diagram of how different things communicate with each other and how we can be incorporating this new service. So the one that so you can see down the bottom, it says proposed implementation. There's something called CAS, Connect as a Service, at the bottom there. That's the proposed, well, it's already a service that exists, and I was proposing that things communicate with this more than what they do today. So it was a proposed implementation. So you probably notice the consistency between these is pretty low. Usually they're just, scribbles of boxes and lines and so on. And that can be hard when you get a big collection of sequence diagrams and system diagrams, which we are starting to collect. My team is starting to collect, more and more diagrams. Different people, I can sometimes, well, actually, there's a few people on the team where I can immediately tell who made that diagram. There's a front end engineer on the team. When he does any sequence diagram or architecture diagram, he uses SVG and he makes like all these pretty like lines between it and really colors, puts all these different colors in it. Sometimes makes it animated, so it's very obvious when he makes a diagram, and it's really cool. But it is inconsistent with everyone else. When I make a quick one, it doesn't look anywhere near as nice as his, and it just becomes a bit difficult to kind of to read and jump between all these different sequence diagrams and kind of to figure out what it means, because you end up having to do with like legends and stuff. You have to have like a legend to kind of say, this is a database and that's a queue and so on. So like there is a bit of a kind of I guess like a inconsistency between all the diagrams, and it can be a bit hard to read because of that. So I've been thinking, what can we do to make diagrams a little bit nicer? So there's something called C4 model, which adds some formality onto the idea of a sequence of a diagram. So it defines different, I guess, like components or different parts of a diagram. You've got people or persons, software systems, containers, and components. And these all have some kind of loose-ish definition, but they do have a definition, some definition at least. And they also have like a hierarchy, like a person can use a software system, but a software system can't really use a person. That doesn't really make sense. So yeah, there's a type of hierarchy, and a container goes inside of a software system. You don't have a software system that goes inside of a container. So it makes like a hierarchy out of things, which is at least some formality. And C4 model, I'm not really that attached to it, but I just like that it has some sort of, structure around it. And, as a Haskell programmer, I like structure. I like having structure on my data. I usually, so the idea is that you've got people, which are users of your system. You've got software systems, which are like, the big kind of named things in your system. Like in ours, we've got marketplace, and that communicates with some other team's system. Usually software system revolves around, team-based type things. My team has this software system, that team over there has some other software system. Inside of that, you've got containers. Containers, are usually the executables or the actual things that are running. So, they could be like Docker containers, or they could be like, Jetty servers, or they could be EC2 instances, something like that. And then you've got components inside of that, which breaks it down even deeper. And I usually skip components because it's a bit too detailed. Components actually usually goes into like, the components, the software, like the actual, what you call it, like the code parts. Like, so, what class names maybe, or you don't have to go that deep, but it's starting to go a bit deep at that point. In the diagrams, the way that the reason why it's called C4 model is that you've got context diagrams, container diagrams, component diagrams, and code diagrams. And because I mostly skip components and code, I don't go that far, but context diagrams and container diagrams are two of the ones that I use, and I'll show some examples in this presentation. Cool. And the good thing is C4 model actually lets you start, because it has some structure. You can start talking about code. You can start representing the C4 structure. The idea of software components and people. You can define this as code, which is great because then you get consistency. It's very easy to update. Instead, like I've had a lot of problems keeping these diagrams up to date because we draw them in something like Glyphy or some sort of diagramming tool. And if you want to update it, you select it and you delete it, and you put another box in there, and you got to draw all the lines up back to the box again. You got to put it in the right place, otherwise it'll overlap. And sometimes you got a name that's a bit too long, and then you've got to change it and move everything around. And it just becomes a bit of a pain to update. And also, it's kind of out of the way, right? You're writing some code, you check it in, you do the pull request, you test it out in staging, and everything. You promote it to prod. Last thing you usually think about is I have to update the architecture diagram. That's usually just not something that you think about. But at least when it's code, we might be able to put it into version control, and people are moving to the idea of like mono repos and things like that today. So if we put our diagrams with our code, would it be easier for us to work with? I haven't explored, the idea of like a monorepo and checking it into our main repository. I do have a repository that I do check diagrams into, which makes it a little bit easier. But I want to explore the idea of maybe having the diagrams in the code base. And so if I want to modify it, I just modify the code and I modify the thing together, which would also mean that we could also tag and release these things. The architecture diagram. I've got version 1220 of Marketplace. And here's the diagram for that. So it can be checkpointed at together. We can release these things together, release the diagrams and the code together, and we can also go backwards in time as well and look at how the architecture diagram has changed over time, which I think would be awesome. I haven't explored this too much, but I do like the idea of code diagrams, these architecture diagrams being code, and also type checked, which is great, and validated. So, type check it, just make sure that, some simple things are good. And then you can do things like validation and say, are there any cycles in my architecture diagram? I don't want cycles in my architecture diagram. So there is, so I've used this library and I've used it quite a bit. It's called Structurizer, and it's a Java and C# library. There's two implementations, one for Java and one for C#. Here's some code. This is some Kotlin code that uses the Structurizer library. And what you might see at some point, let me see if I can highlight this. Yeah, is that working? Yes, okay. So we have, you can see here this line, add tags, and up here, add tags. And also down here, customer.users. So you can see that these are side effects. These are side effects. So we define these containers, right? So you define like this, or you define the software systems and the containers and everything. So you create a model, and then in that model, you do, add tags. And so this defines like it's basically a global state or global mutation. And so when you call add tags, it, adds some, tags to, well, this one's not global, I guess. This one adds tag, but then when you do users, so customer.users, customer application, it basically says that there's a relationship in this global context. And I've actually had, problems with this. One of them is that if I define a diagram and I say, customer.users, the customer application, if I want to generate the diagram and then I want to make a new diagram, like a proposed diagram, which is what I do a lot, right? I have the current state, then I want to generate, a proposed state. When I have customer.users, customer application, I want to change that to, customer front-end application or something. And so I want to switch. I want to change customer. I want to delete this relationship so the customer doesn't use customer application anymore. It uses this one. And because it's in this global state and I can only say customer uses the customer application, I can't say customer doesn't use customer application. I can't do a second side effect to kind of undo this first side effect. So I have had, I have had that as a big issue. I can't really just generate one diagram. What I've had to do is basically generate this massive diagram, generate it once and print it out, reset all the state, like basically clear out all the model and clear it all out, regenerate it again, but make sure not to call customer.users this time so that it doesn't use that customer, it uses the front end. So basically side effects here are causing a massive pain point, and I have had bugs. Even in my, I've had architecture diagram bugs because of side effects. So, people say, you can use side effects very carefully and maybe you won't have bugs, but even in my architecture diagrams, I can't do that. So maybe it's a reflection of me, but I have not been able to achieve, bug-free code with side effects, even for architecture diagrams, even for something so small and simple. Okay, I have a claim, and that's Haskell is great at data. I believe this to be completely true, 100% true. Haskell is great at data. And what are we representing here in this code? Why are we using side effects? Well, we're just representing data. We're really just representing data. I think Haskell is great at data. I'd like to see Haskell doing this. And so this does work. This is some code that I've been working on for a few months now. Very, very, very part-time, but I have been using this a little bit at work. Let me start off with some data definitions. We have the idea of a person, in the C4 model, you've got a person. One of our people is a vendor. A vendor is like someone that actually publishes stuff on our marketplace. Atlassian Marketplace is like it's a marketplace of Atlassian apps. So apps you can install on Confluence, Jira, and Bitbucket, and so on. So a vendor is someone that publishes these apps onto the marketplace. We've got different systems involved. Marketplace is the one that I work on. It's one that my team works on. There's another department called Identity. We use their system, which does authentication and stuff like that. There's another one called Parco. No one really works on Parco, but that's a different problem. But that's a different database that we use. But those are the 3 systems that we use. And so I'm just defining here different systems that are involved in Marketplace. Then we've got containers. So we've got AMKT, which is one of the Marketplace containers, Padres, Asteroids. These are all different services that make up the Atlassian Marketplace. And I'm just defining these here, they're just containers that make up Marketplace. And then, we can define these containers like this. So, container inside of it, like I said, I don't really use components too much, but, I thought here I'll put it in as a bit of a demonstration. So you can have a container that is, a Docker container. Inside of that, you can have a reverse proxy and you can have a cache inside of it. So these are different technologies. I didn't actually show the thing there, but there's a definition of technologies that we have as well. So I define that. Inside of that Docker container, there is different components, HA proxy and Varnish. And if you look down below, you got AMKT with, with AMKT, you have, you've got a Scala container, and inside of that, you've got Scala components inside of it, and web app and analytics are 2 different, things that we run inside of this container. And, I've gone a bit probably overboard with all the type variables here. You can see software system has got 4 different type variables, but I think this is nice. I love type variables. So a software system is Marketplace. So this is the Marketplace software system, and it has these different containers inside of it. It's got the AMKT container, the Atheros container, Hub container, which is Scala, Huberica container, which is Haskell. We do have some Haskell in production. So there we go. That's nice. And then some relationships here down at the bottom. So you can see the relationship. We've got a relationship. We're defining an identity, and the relationship is REST. So Marketplace will go off to identity using REST, and Marketplace will go off to Parco using SQL. Now, because this is just data, we can modify this as well, which I think is really, really nice. And of course, all these symbols and that, this is all Lens. And if no one knows about Lens, that's okay. But really look into Lens. If you want to represent data and you want to be able to easily modify data, Lens is what that is all about. And yeah, so this is the final model. So we're saying we've got all of these different systems involved, and a person called vendor, our vendors, use Marketplace. They manage Marketplace. And once we have all of this code, we can actually go off and execute it. So this is the diagram that's generated from this Haskell code. So this is actual Haskell code, and you can run it, and it will spit out this. So I'm pretty happy with that. I'm pretty happy that this is the way that I'll be able to use. And well, I have been doing it for a little while now. Been defining system and architecture diagrams using Haskell code, which I think is a lot nicer than writing Kotlin and having the mutation and stuff like that. Now, I have started working on adding data flow support. So data flow is this, I guess Sony uses Haskell for some reason, but Sony Xperia uses Haskell, and we've got this data flow library, which is a way of generating sequence diagrams using Haskell. So there already is a library that does sequence diagrams. This is actually, this diagram here is actually generated using plant UML. So my Haskell code prints out like a plant UML, which is like a diagramming system, I guess, like a diagramming software. So it splits out like an ASCII plant UML file, and then I compile it using plant UML, and that spits out that. I've also started working on adding data flow support. So it generates a data flow thing, and then calls this data flow library, which generates a sequence diagram. I have some support for that, but I don't have any good examples yet because it's only partially working. But anyway, I'll have some more sequence diagrams to show soon. The problem with this, though, the problem with all of this stuff that I've been talking about so far is that we're repeating ourselves. We have been writing things like Marketplace uses identity, and Marketplace uses identity, and Marketplace uses Parco, and then a vendor comes and hits all of our stuff, right? So that means we're repeating ourselves because our code already says that. Our code already says, I'm going to go off to identity and I'm going to do authentication. I'm going to go off and hit Parco and I'm going to do some database queries. We already have that in the code. So I've been thinking, why can't we just use this code to implement this? And if we don't use IO to represent our logic, if we just don't code everything inside of IO, which we can do, if we use something like an MTL style, which is exactly what we use at work, we use in Scala, we use like an MTL style-ish thing. Or we use something like a free monet, we can actually abstract away the idea of what we're actually executing. We can say, these are the APIs that we're executing. This is the program is made up of these APIs, and we'll communicate through these paths around these APIs. And then, we can have our test use state T, which is really good. You can mock up the state and everything and execute your program and have it behave exactly how you how you want it without actually executing it. You execute the program in state T. You don't execute it by actually doing any IO, which is great. So if we write our code inside of this, it becomes very easy to know what software systems are being involved when we write it. So this is just a little example. I've made a really tiny example of what I mean here. These are different things that we can do inside a marketplace. So this is like a really tiny version of marketplace. You can create a vendor, you can create applications, you can create apps, which are different from applications and a little bit confusing, but they're a bit different. And then you've got things like you can get the JSON data, because this is going in a website, it's going in a request, so you can get the JSON data out and you can give a JSON response back. Now we could write a program that looks like this, and this is actually executable Haskell code. There isn't like this is taking this API that I've created, and there's a heap of helper functions and stuff I've written, but this is executable Haskell code. You can run this and it will do what you want. It will take the JSON data, it will create a vendor. Once it creates that vendor, it'll get the vendor back. It will use that vendor ID. So you can see here we're using the vendor ID, and we're using the app name. So this app name is coming from the JSON data, and this vendor ID is coming from the vendor that we created. And then we can create an app, and then we can return back the app. So this is executable. You can actually run this. It'll run a HTTP server. You can call this thing, and it'll create an app by creating a vendor first and then creating an app. So that all works really well. What I've done though is made a separate interpreter. So the idea here is that you've got the program interpreter, which will go off and do IO and run a web server called Scotty, and it'll run it all and actually execute and do the actions. But what if we write a different interpreter that takes these API things that we've defined, and they create, so this like for example, create vendor, it will instead translate it into a relationship. So let's say marketplace creates a vendor in the database, or marketplace creates creates an application in the database, or user has requested marketplace. In the case that we get JSON data, that means that user has requested marketplace in some way. And when we have a JSON response that says marketplace is returning a JSON response to the user. So we're creating all these different relationships based on the API that we provide. And this is something that we can do today. Like in my application at work, we use an MTL style. Like we have like M identity, which will go off and do identity things. So we have M Parco, which will go off and do Parco things. So we already know the APIs, and we already have these wrappers around the APIs. And so we could write these interpreters today in our Scala code. And then once you have done this, all you have to do is call, generate sequence diagram on that program. So this is the same program. This is a program that will execute. It will do the Scotty stuff. It'll go off and spin up a HTTP port. It'll actually run and create vendors in your database and everything and so on. And you can have that same program, that same code, go off and generate a sequence diagram. And so that uses this. This is using the Dataflow app, the Dataflow library that I was talking about before from Sony Expedia. This will, takes that program and spits out this diagram, which I think is super cool. So just from writing a program that we can execute, we can then generate sequence diagrams, which I think is super awesome and super interesting. And this is something I want to explore more. I've only kind of got, proof of concept and kind of ideas around this. I don't have, any library or anything like that, but it's something I really want to explore more, and something I think is super interesting. And that concludes my talk.